Hi, everyone. Welcome to the monthly update where I talk about some of the progress that we've been making towards major scientific goals on our roadmap. This is the update for June 2025. And again, this will be a bit shorter than usual as it is summer and many of our staff have been away on leave. Following on from last time, we have continued to fit SAGE 2.3.0, which will be our first force field with neural network charges. Last time, I presented some work that we had to do with cleaning up the physical property data that we were using to fit our van der Waals terms. Since then, we have completed that. We have filtered a new training and validation dataset, and we have refit our van der Waals parameters to those properties. Following on from there, we've also completed a number of valence fits where we refit our valence terms, so bonds, angles, and torsions. And we've now run those through tier 1 of our benchmarks. These benchmarks comprise optimized geometry data as well as torsion drives, and we have identified a candidate that we want to move forward to begin tier 2 and tier 3 benchmarks. So our tier 2 benchmarks include physical properties, so densities and enthalpies of mixing, and our tier 3 benchmarks are solvation-free energies in both water and non-water solvents. Our current candidate improves on RMSD, relative conformal energies, and our torsion fingerprint deviations, as well as across some targeted groups of chemistry relative to 2.2.1. With dataset work, Jen has continued progressing forward the transitional metals single points dataset that we are creating for the Genentech collaboration, where we're working towards a transition metal force field. Again, as a reminder, this is one of the largest datasets we have ever submitted. It's now 68% done. So there's over 400,000 calculations that have completed. And we're also continuing to calculate Hessians of optimization data for open force field. Jen has also been working towards a long-term storage solution for our datasets. So the goal here is to have the data that we use for fitting and benchmarking our force fields, as well as other projects, be usable in a long-term future, where our software, possibly Python and possibly the QC archive have moved on. To this end, our standard operating procedure will be to release all force field training and benchmarking datasets as one unified dataset on QC archive, as well as on Zenodo. The dataset name will follow a particular template. So for example, the OpenFF Smirnoff SAGE 2.0.0 for the data used to fit that force field. And then the Zenodo record will include an SQLite file of all that data, as well as a Docker image with a working Python environment and Jupyter Notebook showing how to get data from the file. We're also looking at uploading Zenodo records of other datasets used around the initiative for force field related work. Moving on to the lipid force field, this project is being driven by Julianne in the Schertz lab, and the goal here is to improve our lipid parameters. As a reminder, our current force fields, so SAGE 2.2.0, do not perform optimally on alkanes. While they get hits of vaporization fairly similar to experimental values, they slightly underestimate densities, and we see much slower diffusion than experiment. Previous refits to additional alkane data continue to overly favor the Gauss conformer in the gas phase as well, relative to the trans conformer. Refitting SAGE just to alkane data did produce energy profiles that matched the QM profile near exactly. But interestingly, despite not touching the non-bonded parameters, this also affected physical properties in the condensed phase. And the alkanes now overly favor the trans state in the condensed phase. Julianne continued to investigate further by refitting non-bonded parameters to physical property data, so to enthalpies of mixing and to densities. Unfortunately, this didn't seem to substantially improve the alkane densities and enthalpies of vaporization post-fit. Julianne is now moving on to a more general plan to refit van der Waals parameters and torsions simultaneously to both QM data and enthalpies of vaporization. Previously, this was difficult to progress because a bug in Evaluator prevented fits to enthalpies of vaporization, but this has now been released in version 0.5.1, which was recently released. Many thanks to Matt and Jeremy at MD Trash for helping us work that out. Moving on to the protein force field, where the goal is to achieve a force field that performs well both on proteins and small molecules. As a reminder, Chapin has invested a lot of effort into different directions here, finding that simply refitting to quantum chemistry data resulted in force fields where the secondary structure of GB3 unravels in solution, mostly this helix highlighted in orange. He's now working in a direction where he refits torsion parameters directly to NMR observables, and he's settled on an approach where he fits iteratively to unbiased MD. We're now in iteration 4, and excitingly, this iteration doesn't unfold the helix in GB3. Chapin has now been benchmarking the performance of previous iterations on other targets, finding that other folded proteins, so BPTI and ubiquitin, don't unfold with iteration 3. That being said, hen egg white lysozyme and the peptide shown here still have their helicity underestimated by the iteration. And he's continuing to benchmark the 4th iteration on these and other targets. He's also moving forward with another direction where he investigates whether adding additional QM data to our initial fitting dataset improves the fit, finding that the expansion of this dataset results in force fields that perform similarly on QM validation benchmarks as the other Smirnov candidates. Okay, so that's some of the work that we've been doing over the past month on our major roadmap goals. Thank you very much for listening, and see you next month.